Hello, so in this problem, we're going to be writing a function that returns true if and only if there exists a path from root to leaf that contains at least n instances of lm in a tree T. So we're going to be defining the function called contains n, and before we begin, we're going to go through the doc test to see what the behavior of this function is. So in the very first line, we're using the tree constructor to create a new tree called T1. The first argument of the tree constructor is the root label, or the label of the topmost node, and in this case it's 1. And the second argument is a sequence of the branches of T1. And remember that the branches of a tree are trees themselves, so we can see here that the root label of this branch is 1, and that this branch has one branch itself that has a root label of 2. So this is what our tree T1 looks like. So when we call contains n on 1, 2, and T1, we're checking to see if 1 appears at least 2 times in a path from the root of T1 to a leaf in T1. So this is our only path from the root to a leaf in T1 because we only have one leaf. And so we can see that in this path, we have 2 instances of 1, so contains n will return true. Next, we call contains n on 2, 2, and T1. We're checking to see if 2 appears at least twice in this path, and because 2 only appears once, we get false. Next, we call contains n on 2, 1, and T1, and this is true because 2 does appear at least once in T1, so we get true. Next, we are going to be creating a new tree called T2 using the tree constructor. It has a root label of 1, and it has 2 branches. Our first branch has a root label of 2 and 0 branches, and our second branch has a root label of 1 and has 2 branches. So this is what T2 looks like. When we call contains n on 1, 3, and T2, we're checking to see if 1 appears at least 3 times in one of the paths in T2. So we can see here that there are 3 leaves in T2. And so we can trace the paths along the branches of T2 from the root to the leaves. So this is a path. This is another path. And this is the last path. So let's see if any of these paths contain at least 3 1s. And we can see that this path here does contain at least 3 1s, so we get true. Next, contains n on 2, 2, and T2 returns false because even though there are 2 2s in T2, they're not on the same path. Okay, so now we can go into the skeleton code that we're provided for this problem. And because trees are a recursive abstract data type, we will be using recursion. So that means we're going to have base cases and recursive calls. So it's actually easier to do the recursive calls in this problem first. And so we can see here that this if statement, elif label t equals lm, will return true if the label of t, remember that label called in a tree will return the label of the root node. So let's look at this call here. We can see that the root label of T2 is 1, and because lm equals 1, we get true for this if statement. So what do we want to do if label t equals lm? Now, we want to check each one of the branches of T2, which happen to be trees themselves, to see if they contain at least n-1 instances of lm, because we've already encountered 1 instance of lm in the root node here. So in order to do that, we're going to have to map contains n onto each one of the branches of T2. And because we're only given 1 line to make a return statement in our recursive call, and we have to go through each one of the branches, we can use list comprehension. So with our list comprehension, we want to map contains n called on lm, which doesn't change, and n minus 1 because we've already encountered one instance of LM in the root node of T2, and B for B in branches of T. So remember that branches of T returns a list of the branches of a tree. So this actually returns a list of booleans because contains n will return true or false based on whether or not we have at least n minus 1 instances of LM in T. So we just want to see that at least one of these paths contains at least n minus 1 instances of LM. So in order to do that, we can use the in keyword to check for membership in this new list that we've created. So we're going to have to check if true is in this list. So if we find one occurrence of true in this list, we know that at least one of the paths contained at least n minus 1 instances of LM. So this is the behavior that we want. Now we can work on our second base case. And because the opposite of label T equals LM would be label T does not equal LM. So that would be if the root node does not equal, the label of the root node does not equal LM. We want to go through the branches of T to see if those branches contain at least n instances of LM. So it's not n minus 1, it's n, because we haven't encountered an instance of LM yet. So our return statement is actually going to look very similar to the one above, in that we are checking if true is in contains n called on LM, not n minus 1, but n, and B for B in branches of T. So these are our two recursive calls. Now we can move on to our base case here. But before we do that, let's look at the base case that has been provided for us already. So the first if statement, if n equals 0, return true. So what this is doing is, remember that n is the number of times that LM should occur, is the minimum number of times LM should occur in a path in T. So if n equals 0, that's saying that LM should appear at least 0 times, and that's always true. So if that's the case, we're going to return true. And we see that this also makes sense with the recursive calls that we make, because we are going to be decrementing n every single time we encounter an instance of LM. Okay, so back to the the base case that we need to define. So let's figure out when we want to stop the recursion. So remember that we're recursing through the branches of the tree. But what happens when we reach the very end of the tree and we get to the leaves? Remember that the leaves of a tree are branches that do not have branches. And a way we can check if a tree is a leaf is to call isLeaf on the tree. So in this case, if the tree is a leaf, meaning that if the tree does not have any branches, we want to check if the label of the tree, which is a leaf, equals LM, and if n equals 1. So we want to do that because if n does not equal 1, if say n equals 2, that means that even though we've reached a leaf, we have not found enough instances of LM in that path. And so because we're only given one line for our return statement, we need to combine these two checks with the AND operator. So we're going to be checking if label of t, which is the leaf, equals lm that we're checking for, and if n equals 1. So let's see what this would look like in this call right here in our doc tests. Contains n called on 1, 3, and t2. So we start at the root node of t2, and we can see that because n does not equal 0 yet, and t is not a leaf because it has branches, we move on to this if statement, and we can see that label t does equal lm. So we're going to return true in, and then our list comprehension. So what our list comprehension will do is it'll check each one of the branches of T2, and then each one of the branches of T2, and it'll keep going until it reaches one of our base cases. So say we've reached this branch of T2 in this call, we can see that n does not equal 0 yet because we subtract 1 from n here when we've started at 3, so n equals 2. So we go to this base case, and we can see that t is a leaf. So we need to check if the label of t equals lm, and that is false. So this statement here will short circuit and return false, which is the behavior that we want if we are checking this branch. Now, if we were to move on to the next branch of T2 for this call, we can see that we're calling contains n on this branch when n does not equal 0 yet. So we move on to this one, and this one is not true because t has branches, so it's not a leaf. And we move on to this one. Label of t does equal lm. So for this branch, we're going to call true in contains true in this list comprehension here. So that means we're checking each one of the branches of this branch to see if there are at least n minus 1 instances of lm in one of the paths. So our first path is going to be this branch here. So we can see that n doesn't equal 0 yet because n now equals 1. So we're checking to see if is leaf of t is true. And because that's true, we go into this return statement and we check that the label of t equals lm, which is true. So now we can also check if n equals 1, and that's also true. So this entire return statement will return true, which means that we have successfully found a path from the root to the leaf of the original T2 that contains at least n instances of lm.